I first want to touch upon why statistics, or why stats. And here's my interpretation about it. We first take a look at the world, or a specific problem that we want to solve. But it mostly applies to, the world and life. I'm quite inspired by many of the statisticians I know. They believe that statistics is the key to solving all sorts of problems, and they believe that statistics is basically this language that we could describe the entire world with, and we could solve all of the unknown problems in the world with statistics. And this is strictly, not strictly, but this is also quite different to what the limitations of mathematics may pose. Because in mathematics, math has a limit towards solving problems or a specific set of problems. Computer science definitely has a limit to solving specific problems. And simply computer science or mathematics cannot solve, or it's just impossible to solve some set of problems that we face in the world, mostly due to the lack of axioms and assumptions that we hold true to math or computer science, but also by the logical reasonings or the logical makings of mathematics and computer science themselves. Computer science, this is most common with the halting problem, as Alan Turing have proved that that we cannot solve all types of problems in terms of total completeness, meaning that we cannot determine whether if a program is going to terminate or not based on the nature of the program without empirical testing. In mathematics, we also have the Gödel's incompleteness theorem as well. However, in statistics is made just as a remedy to somehow overcome that, or it's an attempt to overcome those things. What if we could harness uncertainty and extract the truth from that uncertainty? So the world is filled with knowledge or facts that we do not know. So we're facing the unknown, and we would say that this is a cloud of noise, because we don't know the nature of this logic, and we could even connect this as what we call as a fuzzy logic, where we do know the overall gist of this fact or truth or this type of system that we know, but it's mostly in a cloud. It's opaque, it's foggy, we don't know its ins and outs, or the overall patterns, or the overall construct, or the nature of this type of fact that we see. And this is why we call this as fuzzy, because it's a cloud, and we don't know what's going on. It's just fuzzy, filled with noise, something that we cannot see, something that we cannot touch, something that is just unknown to us. And mathematics and any type of other science has a hard time providing some objective truths or observations or proofs towards identifying the nature of such kind of system or of such kind of fact. So this is why we're calling it as fuzzy. Statistics is meant to model this. It is meant to identify some sort of natural properties of what this fuzzy logic may have, by simply assuming that it is okay to be fuzzy. It is okay for us to not understand everything. Just let it be. Instead, we would try to understand the cloud itself. And then try to interpret what the nature of this cloud is. So what's the nature of this cloud? And this is all about statistics. This is what statistics is all about. And it is a branch of, or I cannot say it's a branch, but it does connect to empirical sciences, where empiricism is about what? Testing. It is a glorified key term of the phrase monkey with a wrench, where we don't know about the elegance of this fuzzy logic. We don't know its nature, so therefore we're not elegant about our definition of a specific fuzzy logic, or we do not have an elegant explanation nor a provable explanation about this type of logic or system that we're trying to understand. So we are basically a monkey with a wrench. We are these primitive monkeys who have no idea about what this thing may be, or we cannot explain it, but we do have a wrench where we could just smash it and see what pops out. And this is the idea of empiricism. We're trying to empirically test this type of fuzzy logic, put it to some type of a test, smash here, smash it there, see what pops back out, and try to understand it by that idea only, and try to extract some type of truths that this fuzzy logic may yield by doing these controlled experiments and these controlled tests. And although we will never, or we cannot be able to fully understand the inner workings of such fuzzy logic, at least we would approximate the nature of such fuzzy logic through empiricism, testing, and just figuring out what pops out, and if we smash something in, or which buttons work in correspondence to one another. And again, this is what I'm talking about, and this type of notation is what we can call as correlation. If I press one button, if I press the red button, I observe that the blue button just pops back out. And if I press the blue button, I observe that the red button pops back out. We can at least say then, therefore, that the red button and the blue button are correlated with one another. They're somehow related with one another. And we want to determine whether if, for example, that these are causal, meaning the pressing of the red button solely causes the blue button to pop back out. Or we might not be able to determine that if there are many more buttons. Let's say there's a green button, a yellow button. But just because pressing the red button and that the blue button pops back out doesn't mean that the red button and the blue button are directly causal to one another. Maybe there is another inner working that is a lot more complex, in a way that maybe the red button and the blue button aren't causal, but they are related in some sort of way. We will never know. We will never know that by testing. We will never know that as monkeys with the wrench. But we can make some other specific tests in order to determine whether if the red button or blue button are causal as well. For example, we could test the pressing of the green button while keeping all of the other buttons constant. And by producing these controlled experiments, we should be able to determine what the independent variables are and what the dependent variables are and what the control is. And you may have also kind of learned that in high school or middle school science classes, where when you're trying to conduct an experiment, we would like to divide them as independent, dependent, and controlled experiments. And the overall idea of causality and correlation is highly discussed in statistics as well, because again, statistics and empiricism, they're very much related. Statistics is also a glorified mathematical definition that explains or justifies the monkey with the wrench approach, or empiricism, as we might call it. So by collecting data and by collecting these testing data, we would like to mathematically model and identify the specific nature of this so-called fuzzy logic, or something that is unknown, but we could test it in the surface. In many other cases, we may not be even able to test this type of fuzzy logic. It could be in terms of medicine. It could be in terms of a survey. For example, we would like to understand the proclivity towards buying a specific product based on the product's location in the supermarket, or based on the quality of the product in the supermarket. Although, if you can think about that, there is some extent to produce some experiments with that. It is most likely the case that we would be able to conduct surveys. Another better point of view, I guess, better example. I stand corrected on working on that Walmart example, but in a better example would be political votes. Like who's going to be the next president, and trying to understand what the votes may entail. And while trying to do so, we cannot perform experiments. It will most likely be an observation. And let me just write that down, because that is also quite important. An observation. So an observation-based analysis. So by simply observing what is going on around the world, we would like to determine the nature of such problem that we're trying to identify through observation. Maybe it's the votes, right? We only have to observe. It is very difficult, if not infeasible, or if not quite unreasonable, to produce some type of an experiment for determining who is the next president of the United States, or who's the next president of Korea, or something like that. We just simply observe, simply survey people and say, who are you voting? And by understanding that, we would like to somehow mathematically come up with a conclusion or an analysis in how confident are we such that a specific president is going to get elected. Is it significant enough? Is it overwhelming? And if it is overwhelming, how much is overwhelming? What is the definition of overwhelming? Is it 60-40? Is it 70-30? Is it 80-20? Is it 90-10? Is it 99-1 in terms of ratios? Like, to what degree, to what extent can we define it to be overwhelming? And what does overwhelming mean? Does it mean that this president has currently so many votes that it is almost very, very likely that this is going to be the next president, that he is going to be the next president, or she is going to be the next president in the upcoming vote? And to what degree is very likely? Is it 90% likely? Is it 80% likely? And how can we quantify those things? How can we determine those things? And how can we justify that these percentages, or this kind of probability or likelihood that we have kind of defined or kind of stated in our analysis, how can we justify all of that? And is there a mathematical justification for this? And if so, what are some of these models, and what are some of these concepts or theories in mathematics can we use to determine the validity of such likelihoods? And that is the overall idea of statistics. So we're trying to provide some kind of a mathematical wrapper around fuzzy logic, or a mathematical wrapper around uncertainty. Leave the uncertainty as it is. Don't try to probe it through, because it is very, very difficult to probe through such fuzzy logic. Because there's so many unknowns that we have in our current knowledge, or in our current technology, that we cannot fully identify such type of fuzzy logic as well. And therefore, we would try to identify just what this fuzzy logic is, and what's the overall nature of such fuzzy logic. Okay, so these are some of the overall big pictures that we want to understand. So all in all, one summary, we would like to mathematically identify or describe the unknown, something that is unknown. Okay? So it's a little bit different to what we kind of learn in school, or it's a little bit different to what we learn in school, because all of the things that we learn in school, in fact, are based on discoveries that are more or less proven to be true, that already has an answer, and that there is no such thing as fuzzy logic. There is no such thing as uncertainty to the concepts that we learn in definitely in middle school, definitely in high school, and also in university. And although I am being very, very blunt and curt about that, and of course, things that we learn in high school and university are ongoing subjects of discussion, ongoing subjects of study, meaning that they are bound to change, meaning that they are changing, they're dynamically morphing. There are many other discoveries that we have made in recent times, and there's continuous discovery that could contradict to what we have learned in high school a few years ago, or that could even augment some of the concepts that we have learned a few years ago as well. And this is what we have to keep in mind while studying in high school and university, is to understand that we're in the process of studying these things. We're not, there is no answer. There is no direct answer in all the concepts and knowledge that we learn about the world. We have to, in fact, question and suspect all of the concepts that we have learned and fully understand and appreciate some of the explanations and justifications that other great scientists, mathematicians, or theorists and philosophers have made about some of these concepts and trying to explain some of those concepts. And basically understand where they're coming from and put that into our knowledge and make it our own. And possibly, and I also recommend that, for us to also contribute to this pursuit of truth and knowledge. And I would say that statistics is also a wonderful way to kind of get engaged on that. All right, so this is what I have kind of talked about. And now let's just go into this idea of how do we understand uncertainty. Okay, how do we try to describe uncertainty? Because what's uncertain is uncertain, and therefore there's not much that we can work with, right? We have so little that we understand. What can we work with? And that is a very good question. That's also a very good point that we also have to appreciate. There's not much that we can do in terms of completely understanding the truth. But we can understand, for example, what's the center? What's the locus? Locus means center, or it could be the center of discourse. What's the main idea, or where is the center, right? So we could determine the center or the locus of fuzzy logic. And we could understand the extent of its influence. How much does this fuzzy logic extend in its influence, and to what degree, or what's the limit or the upper bound of which this fuzzy logic will have its influence? Maybe up until this type of distance right here, maybe the fuzzy logic cannot influence anything at all, or it is so negligible that we would just kind of provide a virtual upper bound and say that, oh, this is the limit to the extent of such fuzzy logic. And defining those boundaries, we're talking about boundaries here. Defining these boundaries and the center of this fuzzy logic is also pretty important. That is because we can finally determine what's the limit to this fuzzy logic and where does this fuzzy logic lie in our knowledge and in our in our kind of discourse in discussion or arguments or in conversations or in logical statements, right? To what extent does this fuzzy logic apply? This is also extendable for political votes as well, and I'm just keep on butchering this kind of example of political votes because currently this is what I can think of. I'll think about it more in the next upcoming series, but for now, political votes make a lot of sense. To what extent is does this kind of votes determine an overwhelming majority. That would also entail the upper bound or the limit of some votes that are needed for this presidential candidate to succeed or to fully guarantee that he or she will become president. And what is the exact number of votes that would guarantee that? And how do we know that? And this is most likely by calculating and understanding the extent of this influence in question, or what's the boundary or the upper bound. If we can just go beyond that boundary, we should be able to secure some type of outcome or some kind of a winning vote. And this is what boundaries do. The locus or the center determines the anchor point or the baseline of where this type of logic in question lies. Like, what's the baseline of the votes? What's the offset of the ratio of the votes, and how do we determine that? And all of those things it's powerful if you think about it. And there are so many ways that we can work with just by understanding the locus, the center, and the extent of influence. And we should be able to determine a lot of things that were surprisingly unknown to us, and just by how little that we have in terms of fuzzy logic, how little truth we have in terms of fuzzy logic, we should be able to determine a lot of surprisingly new facts and analysis about this type of fuzzy logic that we first initially appraised to just contain nothing but garbage and noise, and basically just simply garbage in our data. But by analyzing through statistical concepts, we now further appreciate that there's something more to it, and that we understand this in a much better way. And that's the, I guess, beauty of statistics in its best form. We get to know a lot more things, even by using the unknown, even by working with the unknown. And that is why proponents of statistics believe that statistics is a very, very powerful tool, because if we only work with uncertainty and yield such great results, what would happen if we work with completely certain parts of logic? What if we could just use them in terms of truths, only truths, and something that is very much well studied? And what if we could just apply some type of statistical analysis with it, and that would just make it a lot more powerful? But again, this is more about I'm just talking about in terms of motivation, and this is what makes people pumped up about statistics, rather than the actual an argument for why statistics is actually is the most powerful logical and mathematical tool ever invented. Well, I say it's not. It's the same as mathematics and science, but it's cool to understand statistics in this kind of way. So again, let me just put this in bigger words. We're trying to understand the center, and we're trying to determine the boundaries. And this is what statistics is all about: the center and its boundaries. And how do we do that? How do we determine that? And let's just now introduce some models that we can now finally model fuzzy logic in itself, right? What are some models that we could mathematically quantify fuzzy logic in terms of center and boundaries? Well, we first need a mathematical model that could yield a center, and that could also yield some type of a boundary. And boundaries, I mean not hard boundaries, meaning there is a hard threshold where it's black and white. Maybe that, this is within the boundaries or this is out of the boundaries, 1 and 0. I'm not talking about this type of boundary, meaning I'm not talking about this binary boundary where it's all or nothing. We could even produce a kind of a function for this type of a hard boundary. And we should appreciate a lot more of how strict and black and white this type of boundary is. For example, we could create this type of a function where this is hard, where everything below the boundary is 0, meaning that, it is let's just say that it could be an inverted one, but let's say 0 has an interpretation of it is within the boundaries. Although, numerically, I don't really appreciate that. I would rather much appreciate an inverted step function, for example, in terms of what we're trying to do. Let's say, let's work with this. And although I'm kind of being redundant, but I'd say that this should do the trick. So let's say that 1 it's within boundaries. It is true that it is within boundaries. But given a specific threshold, it suddenly jumps to 0, where it is out of boundaries. And the reason why these black and white or hard boundaries are bad is because we're dealing with uncertainty. We're dealing with the unknown. How can we fully justify that at this specific threshold t, or we could just say threshold, that the overall fuzzy logic is within bounds or it is out of bounds? How can we specifically determine that kind of threshold with such precision and with such accuracy, such that we can just make it as completely black and white? Because you have to also appreciate that we are dealing with the unknown. There could be uncertainty into our boundaries as well. There is uncertainty in our boundaries. We cannot just say that there is a hard threshold. Or else if we can determine a hard threshold, it must be justified and it must be proven that this is the hard threshold and this is where it is within or out of boundaries. We need to prove that. But this becomes now a contradiction in general terms, because how can we prove something that is mostly unknown? How can we prove something that is unknown, especially within its boundaries as well? We don't know the extent to its fuzzy logic. We just kind of understand the overall boundaries of this fuzzy logic. We don't know the exact boundaries of that such kind of fuzzy logic. If we need to understand the exact boundaries of fuzzy logic, we need to understand the exact inner workings of that fuzzy logic, so that we could finally pinpoint it and say that this type of knowledge proves or indicates that this specific threshold is the boundary to which this logic is applied and not applied. But since we cannot pinpoint it, we simply have to approximate it. We have to approximate the extent to which such fuzzy logic is going to extend itself, right, in the overall knowledge, in our network of knowledge, or in our discourse, in our discussion, or in our arguments. We need a softer bound. So since we do not know the exact knowledge that defines a threshold, so this is why we have a soft boundary. And in all of statistics, we use a soft boundary. And I would also argue that if there is a hard boundary, then it doesn't really kind of describe what statistics is all about. But again, knowledge is fluid, meaning the ideas and most of the overarching value of statistics can be applied to these hard set boundaries, or to even ideas and theories that have been proven and that already have a concrete discoveries and evidence and facts and truths that fully define that specific type of study or knowledge. Like, we could even apply statistical concepts with such hard bounds. And in fact, thinking about that, I stand corrected, meaning statistics is not just about soft boundaries. It is also available for hard boundaries as well. And I believe that this could be somewhere that we could also study in. Like, how can you apply statistics, and what can statistics do better in where boundaries are hard, where boundaries are proven? And what can we learn more about it using statistics? And I think that would be a very interesting type of thing that we will learn about. But let's just first focus on the soft side, because since we're working with how statistics may be since we're discussing about how statistics works in terms of uncertain, fuzzy logic, where we want to focus on that a little bit more. Let's go a little bit more in depth about how we can work with fuzzy logic. And since we're assuming that we're dealing with this type of a fuzzy logic problem where we do not have enough knowledge about that type of fuzzy logic to determine or pinpoint a specific knowledge that determines a said threshold, we would just rather make it soft and say that, hey, we don't know the exact knowledge that would prove a specific threshold, so let's just give it a softer threshold. And I guess then the assumption would be to model it somewhat like this, where since this is 1 and this is 0, and this is basically the overall idea, where this is 1 and this is completely 0. And again, as you can see, we're appreciating that this is a dropping in terms of a slight gradient. It is dropping softly rather than a hard threshold. And this kind of gives us some type of an advantage. One, we don't need a threshold. Like, we cannot just define a threshold given that this is soft. So this soft type of boundary would kind of give us that kind of an assumption that, hey, we don't need a threshold. Instead, we are putting some kind of a model that shows that, it just decays. The overall boundary decays as the distance from the specific center or the locus increases. And that makes sense. That does make sense in an intuitive way, because the farther we are from the center of discourse, or the center of this sort of the origin of such fuzzy logic, the less certain we are about boundaries, and the weaker the influence of that such fuzzy logic may be. And this is why we're trying to prove that we're trying to identify this as some kind of a softer boundary as well. And notice that I didn't model it in terms of this, right? Like a linear, like we never did linear. Instead, this is more of this is specifically a sigmoid, where, again, we could just talk about it as some kind of an exponential. This is an exponential. And the sigmoid is basically what I drew. So there's a little hump, and it just kind of does that. And so this is an exponential decay, and this is what we call as a sigmoid decay. Or if you might kind of model this in a different way, you might have kind of saw this in chemistry or physics. This is also what we call as sigmoid, which is bounded by 0 and 1. And as you can see, it behaves a little bit differently than an exponential. An exponential would simply do this. Let's say that this is 1, it would just simply be monotonic. It would just increase. Although sigmoid is also monotonic, like an exponential would just go through the roof and it would just skyrocket. But a sigmoid kind of plateaus in a specific upper bound and plateaus in a specific lower bound. And this is not intentional, this is intentional. And there are other models that we can learn in terms of describing a specific distribution in terms of exponential decay or in terms of sigmoid decay. And again, these are models. And I'm talking about models a lot because it's a choice. It's a choice. And models make different assumptions. About, I would say, the nature of said fuzzy logic. We make different assumptions about the nature of it. Is the shape, is the identity of a fuzzy logic exponentially distributed or distributed in terms of a sigmoid? is the boundary of this fuzzy logic determined in the shape of an exponential, a linear, or a sigmoid? And mostly we don't really care about linear. We don't really work with linear, and there is a reason for that. It's because a linear type of decay needs to have more facts and figures that directly prove that, hey, this fuzzy logic has a linear decay in terms of its boundary condition. But most of the things that we would learn will never be linear because, again, like we have said, linear needs more, I'd say, facts or ground or knowledge or truth. But again, this kind of deviates from our topic of discussion, which is fuzzy logic. We're assuming that we don't really know, or in fact, in terms of college courses and high school courses, we in fact assume that there is nothing we know about in terms of this fuzzy logic. We only have data. Like, it's purely based on data. We only rely on data, and no background, or I would say minimal background. But again, at least from what I have learned in Stat 231, we don't assume that. We don't assume that there is no background or minimal background. There is, or we are indeed encouraged to understand the background. Like, what's the context of this data, for example? What's the background of this data? And by understanding that background or context of data, we would be able to now give educated decisions and choosing whether if we would like to use an exponential model or a sigmoid model or a linear model and that kind of thing. Because now we would be able to conceptually identify the nature of the said fuzzy logic, and therefore we should be able to choose the right model for that fuzzy logic. And again, this is why we have a lot of models. Again, a model is what? A model is a definition based only on assumptions. And therefore, can we say that one model can describe everything about fuzzy logic? Any type of fuzzy logic. You give me any type of fuzzy logic, there exists this kind of a single model that will be able to describe all types of fuzzy logic. I mean, it's slightly debatable based on the definition of what a model is. If such universal model exists, then could we even describe or define that to be a model? It would simply then be a universal truth, a truth that is applicable to all types of fuzzy logic, right? But a model is simply based on, but again, it's based on the definition of a model and the practical application and what we think of models to be. But in most of the cases, at least in my experience, in all of the cases, models do not explain everything. Models only explain a small substrata of fuzzy logic. And models have a hard time or are just inaccurate in explaining fuzzy logic that is outside of its strata, that is outside of its domain of discourse or outside of its assumptions that it make. Because, let's say given a set of assumptions, not all of the fuzzy logic will apply to those specific types of assumptions. Or even if those assumptions have been met, maybe some other forms of fuzzy logic may require other types of assumptions to make a more accurate and precise prediction or analysis or definition of such fuzzy logic that we're trying to describe. Maybe there is more context that we know. So we cannot say that one single model, right, is going to describe every type of fuzzy logic. And in fact, that's what models are for. Models are simply used to approximate and just kind of bluntly describe a fuzzy logic in a predictable way, such that it is easy and simple for our small monkey human brains to understand and reduce all the complexities of a fuzzy logic that could possibly give us that would give us more noise than useful information. And noise meaning false discoveries or false conclusions or false analysis because of some type of a noisy signal that we deem it to be true. And there are many cases like that. Possibly a blinking light may give us some kind of a notion that this blinking light may be very significant and could describe some truth about some type of a phenomenon, but actually the blinking light may be simply a noise. It could be some kind of a random blinking light where we scientists have just simply attributed it to be something more divine and something more meaningful and more significant, that it could describe some type of this device or system or truth. So again, we have to also kind of be safe about it. We also have to filter out things that are noisy, things that could give us false conclusions. We would like to eliminate as much false positives or noise as possible, and to maximize our discovery of truth and discovery of information, useful information. And this is what models kind of help us do, because it kind of simplifies things for us. With the cost of maybe, not being able to analyze some of the important truths that we might collect or come up with or discover. But again, it's like a trade-off. So these are what models are for. And in most of the cases, I would say, let me just end it here and just give you a lot more food for thought on this. And then we would go into basically all the nitty-gritty mathematical details of statistics and what are the applications of statistics, such as determining what we have discussed in the earlier parts of this section is correlation or causality. We could even determine that just by understanding the center and its boundaries by using some kind of a model. We could also determine what we can call as hypothesis testing, like how confident are we or how certain are we for a specific political candidate to be voted as president given a specific situation of the vote counts. So, those things. So that's called hypothesis testing. And we would also discuss many more models as well. So that's the overall agenda. But in many cases, the big picture stays the same. We're trying to understand all of these stuff that I have just mentioned by only working with center and boundaries. And also, like we have said, since we're dealing with models, since we're working with models, we also want to determine whether if a specific model that we have selected for a fuzzy logic is the right model. Is it the best model? And how can we determine that? right? How can we identify that this specific model is the best out of all of the classical models that we will learn in our short statistical tutorial or our short statistics tutorial? And there is a way to mathematically quantify that. And this is also called as the goodness of fit test. And again, all of the things that we will learn will be based on a single mathematical framework that we're going to develop throughout this tutorial section. There will be a mathematical framework, an overarching umbra of this kind of a mathematical framework that kind of secures us, that kind of builds a fence around us and say that within this fence there is a lot of certainty and truth behind it, and this is what we can work with, type of thing, right? This is what we can work with. Everything that we are working with in this kind of a sandbox is true. Therefore, we could express a lot more creativity in applying those types of models. And these are what we're trying to deal with. And again, the goodness of fit test models, like these centers and boundaries, whether if it's hard or soft, the choices of these specific models, and the hypothesis testing that we've discussed, the correlation, the causality, and also the, it could be much more other things that we would learn in the statistics tutorial. All of these is based on this single mathematical framework that we would kind of discuss. And that is basically the overall agenda. One thing that I would also kind of introduce in terms of models is what you could have also discovered in your high school or middle school or possibly college statistics class, big introduction to statistics class, and is called a normal distribution. This is a horrible normal distribution, but again, this is what we kind of use as a staple. It is basically the norm of all models, and there is a reason for that. And most of you might kind of, not most of you, but some of you might understand this as the central limit theorem, where it means that any type of distribution, any type of fuzzy logic, and this is mathematically proven, any type of fuzzy logic, right, is somehow indirectly related with normal distribution. It is indirectly related with the normal distribution. So you could technically, if you do some linear transformations or linear or nonlinear transformations on a fuzzy logic, you will end up with a normal distribution, or you can end up with a normal distribution. It is possible for you to end up in a normal distribution if you do a specific sequence of linear or nonlinear transformations of a specific fuzzy logic. And this is fascinating, and this is very interesting, and this is called the central limit theorem, and it's a theorem because it is proven mathematically. And why is this interesting? We at least have some type of a universal framework to fit a model, right? We have some kind of a unified model, a universal model that could describe possibly any type of data. And then you might get hyped and say, hey, then isn't the normal distribution the universal model? And you will soon appreciate that in many cases it is, but since we are performing these linear transformations or nonlinear transformations, we are indirectly attributing a specific normal distribution with the true fuzzy logic. But if we want to understand the true fuzzy logic, there will be limitations. Again, like all models, there will be limitations in describing a transformed fuzzy logic in terms of a normal distribution. So again, like if we can just draw it in terms of a picture, it is like this. So we have a fuzzy logic. We do a transformation. So we do some kind of transformation, and we get a transformed fuzzy logic, and then we then model this into a normal distribution. And by the way, another name for normal distribution is called the Gaussian distribution. And the reason why it's Gaussian is because Gauss discovered, or somehow was one of the first to identify this model called the normal distribution, or come up with a mathematical formula for this normal distribution. Right here. And so, as you can see, we undergo this type of a intermediate transformation, right? We have an intermediate, and the normal distribution describes the intermediate, but again, since this is only an intermediate, we do not describe or directly describe the nature of the fuzzy logic itself. It is somewhat indirect. And again, if we can find a inverse transformation, then it'll be great, right? Then we can kind of decompose or deconstruct this transformed fuzzy logic, this intermediate, into a truth. But again, we would now, as we move along this course, we would finally appreciate that the specific transformation that we do in order to describe into a normal distribution, this specific type of transformation doesn't necessarily have an inverse transformation that can fully describe this fuzzy logic from the intermediate. That also means that this transformation that we do is just unidirectional, meaning it's just one way. So if we encode a fuzzy logic into an intermediate transformed fuzzy logic, it is difficult, or if not impossible, to fully reconstruct from an intermediate into the full fuzzy logic. This is why we call it unidirectional and not bidirectional, meaning we cannot just go back and forth. This also means that such transformation is a lossy transformation, meaning we lose information. We lose information about such fuzzy logic while trying to transform into the specific intermediate. That also means the transformed fuzzy logic is this intermediate is a simplified version. It's a truncated or a summarized or a simplified, generalized version of a fuzzy logic, right? And since we have lost information, we cannot come up with new information just by simply performing transformations. We need additional bias or additional information or context in order to fully reconstruct this intermediate into fuzzy logic. However, that using simply linear or nonlinear transformation without any other preconditions or assumptions, that seems likely to be impossible. So again, this is why the normal distribution, although it seemingly looks like to be universal and it can describe any type of data, the same problem arises, meaning the same limitations of what a model is stays the same, if not worse, because normal distributions, they pose more uncertainty. They pose uncertainty about fuzzy logic, because if the fuzzy logic cannot be directly encoded into normal distribution, we have to first encode it into an intermediary, thereby losing a lot more information and thereby losing a lot more precision and accuracy for this normal distribution model to correctly describe fuzzy logic. So there is some kind of a trade-off between them. But again, we will be discussing this a lot further. But I was trying to give you allude or foreshadow this type of model's limitation type of idea, and why normal distributions, although a normal distribution is the closest that we have got in terms of classical models to be a universal model, it is actually not as great as it seems because of these certain specific types of limitations. And again, I mostly focus on these types of limitations because this is mostly overlooked in many cases. And thereby understanding these limitations, we would get to truly appreciate what statistics is all about and how can we work around these types of limitations. And that's actually, I would say, the beauty of statistics, like using our creativity, of course, within the bounds, within the fence of this umbra, of this mathematical framework that we'll develop later. How can we use our creativity to better describe a specific fuzzy logic or some type of a problem that we wish to describe using statistics? And I guess that is the beauty of it, and that is where all the fun and all the goodness in statistics comes alive. And I hope and we're looking forward to for all of us to kind of appreciate that. And yeah, that is about it for this section, and I will visit. We will meet again, and while discussing more about the details of models and the identity of models, what are the attributes of models, and some nomenclature that we use in statistics to give us some more, I would say, jargon. To give us more jargon to discuss more in terms of statistical terms. But again, at the end of the day, this is what the overall picture of statistics is. All right, I'll see you in the next video.